Hi everyone. A couple of videos ago talked about the covalent bond and how when two atoms separated in space come together, their orbitals overlap and basically create two combined orbitals separated by an energy gap called the exchange energy, and the two electrons that are associated with those orbitals then fall pair in anti-parallel states and fall into the lower orbital, leaving kind of that upper orbital empty. Well, when we talk about a crystal, we have the same kind of thing happening, just multiplied by a lot. And so, basically have a similar picture where we've got, initially we've got a 1s and a 2s state, for example. And imagine we bring this crystal, bring all the particles closer together. These orbitals start to separate as they start to overlap, and basically an equilibrium state is reached, just like when we have a covalent bond. And so this represents the distance between the atoms in a crystal. And also, instead of having just a single energy level, we now have an energy band, right? This is really, this has got like 6 or 7 lines, but really we've got, millions of lines here separated. And so we've got almost a continuum spectrum here, and then another one up here. So if we've got electrons in the 1s orbital, maybe we're talking about lithium or something, I don't know. Bring them all together, those electrons will fill this band. There will be nothing up here. And this picture then represents the situation, right? We've got a band instead of an energy level, an energy band in which all the electrons are filled, and a conduction band here, which is empty. Now this is the situation for an insulator. And the reason for that is that in order for the electrons are all locked in that valence band. They're stuck where they are. They're at their lowest possible energy level, which means they're not moving. In order to move, they have to get a little bit of energy. Problem is, there's this big gap here where it's not possible for an electron to be. So, in order for the electron to move, it can't just get a little bit of energy. It's got to get all of this energy from somewhere. And heat is not going to be sufficient. It's going to have to be, some sort of input of energy in order to get an electron from here all the way up to here. This is why in an insulator, the electrons don't flow very easily. Of course, it's possible to get them to flow, but you have to insert enough energy to get the electrons up into this conduction band. Now, a semiconductor closes this gap a little bit, and a metal is when the bands actually overlap. And so in this example here, imagine this were a little bit closer, right? Or we're a little bit higher up the chain, which is true for metals, right? Maybe we're talking about the 2s and the 3s orbital. You imagine that maybe this spread, they actually start to overlap at the equilibrium state. When that happens, then there are electrons here, and the amount of energy required to get into the conduction band is practically zero. All they got to do is hop up here, and then they can start to move. That's why a metal easily allows the transport of electrons, because that conduction band is easily available. Now, why is a semiconductor so important? Isn't a semiconductor just another insulator? It's weaker, I suppose. But what makes it so special? The thing that makes it special is that this gap here is small enough for thermal energy to be sufficient for the electrons to jump into the conduction band. So what I mean is that just being at room temperature, there's enough kind of intrinsic energy, the internal energy of these atoms is just enough for these electrons to pop up here to the conduction band. So what I'm saying is that at absolute zero, there are no electrons in the conduction band. They're all in the valence band. But at room temperature, there's always going to be some distribution of that energy. Some of the electrons are going to have more energy than others. Those that have more will be naturally in the conduction band, which means that there will be some flow of current possible in an induction band. Whereas in an insulator, it's kind of a yes-no situation. In a semiconductor, it gives us a situation in which at room temperature, we can have, a little bit of having our cake and eating it too. And we'll see how to utilize that going forward.